is thanks to Bram van der Akker and John Smith. They are both senior machine learning scientists at Booking. And probably we have all experienced that the ETL process sometimes in our jobs can become somehow messy, especially as the company grows or if the company is larger. Fortunately, they are going to tell us about the concept, tables as code. So the floor is yours, guys. Thank you for being here.
So before we get started, I would like a quick raise of hands. Who works or has worked with ETL workflows or, yeah? Okay, keep your hands up. So if you feel that you test your workflows before production enough, you can keep your hands up. Okay. And now I had another question, but that one I forgot, so you can all lower your hands. So let's get started. My name is Bram. John, we've already been introduced, so let's keep the small talk here. We do represent a larger group of data scientists, machine learning scientists, and engineers, which are all here on screen, and probably some are in the room. You can raise your hands if you want. No? Didn't show up. Fine. So, data at Booking. Why we as Booking.com are standing here in front of you to talk about data or data engineering? Well, we have dozens of teams working on generally data exclusively. Oh, there you are. Why didn't you raise your hand? We have dozens of teams working on data, which makes for hundreds and hundreds of data practitioners all around the company, in largely Amsterdam, but also largely outside of Amsterdam, producing thousands and thousands of data workflows, resulting in tens of thousands, if not hundreds of thousands, of data assets. And in all this, mostly in this talk, we face a common data headache, data design headache, and we'll discuss that now. So let me explain. So it all starts with persistent data. So if I talk about persistent data, I generally talk about things stored in S3, HDFS, but it can also be part of Hive, Snowflake, Presto, whatever you run. And all of this data tends to be produced or consumed by some form of code, obviously. This code can be Python, which probably most of you do, but it can also be SQL, it can be dbt, it can be Spark, it can be any language. We're going to talk mostly about Spark and Hive, but it would apply to any other combination of persistent data and code. Now, persistent data and code live in very different worlds. Code on the one hand, persistent data on the other hand, and they don't really touch unless the code is executed in production. And what happens is that through this, producers and consumers of data only communicate through the persistent data in production. For example, in Spark, if you write a data set, you simply give your data frame, give a string location, bam, placed in production, placed in the persistent data world. And reading the same way. But there's no guarantee that what you expect to read will actually come back. As a result, changes are only really tested through this persistent data in production, leading to some form of a YOLO deployment in many occasions. So what we need is a contract between the consumer and producer that lives in the land of code, not in the world of data. And this brings us to the title of our talk, Tables as Code. So a real brief structure of the talk. I'll first introduce what are tables as code, so you have a little bit of an understanding of this, and then we'll talk about some of the advantages. Customization of data access, testing made easy, probably the most important part. How you can use these tests to build and deploy easily, and also how to scale these builds when you get to thousands of workflows. And finally, a very important part of this is scaling the community, because this only works not only in scale of data, but also in scale of community, which you understand throughout the talk. So, a table as code is simply a contract, you could see it as a contract, that lives in the target language. So it could be Python, for example. When we access our persistent data, we always want to flow through this particular contract. So all of the writes and reads go through this particular contract, and the contract looks something like this. In our case, we've designed it as a class. So the class here is a Hive table representation of a table called hotels. We have a schema defined in the class, and as you might be using schema registries, this can also be synced with the schema registry, either on read and writes or in another way, but importantly, this exists in your code. It's not exclusively on your persistent data side or exclusively in your data registry. And we also can add any arbitrary other type of metadata, like format, location, partitions, or anything we would like. And now as developers, we can control the interface of this data asset. So here, we've extended the class with a write method that takes the class and, for example, checks the schema compatibility. So before we write, we check the schema compatibility, both in production, but also when we write test, integration test, unit test, anything. Always, this is executed. And we can extend it with any arbitrary hooks we'd like. So, for example, think about in-code data validation. Instead of relying on first writing to a big, big staging environment, we could, for example, test it in tests. So in unit tests, we could also check our data consistency. We could redirect source and targets. So when we don't have access to a staging environment, like we don't have in Booking, we can simply write from certain machines to a personal schema in our production environment that is shielded off. And also, we can introduce any custom write strategies on top of whatever language we use. Think about atomic writes or incremental writes. Anything we'd like to customize, we can make part of this object. Now, what happens is when we want to use this contract, we simply import it as a class, and both producers and consumers can access the interface that we as developers create and write through this contract to our persistent data. Now, this is the design principle. That might sound very interesting, but it really only becomes interesting for real if we wrap this all into a monorepo. And this will be John's part of the talk. John, fire away.
All right. Thank you very much, Bram. I want to talk about monorepos. Specifically, this is going to sort of close the loop on exactly, we talked about the principle, but how do we do it in practice? The answer is a monorepo. Now, the word monorepo might raise some sort of negative or fiery emotions in some people in the crowd. And there might be a debate that ensues the moment that I get off the stage. I would like to, for the next about 23 minutes, close that debate. And then just say, okay, if you like polyrepos, that's okay. We can settle our differences, maybe like over drinks later. I want to talk about this, what's in this monorepo precisely. First, I'm going to talk about local testing. Then I'm going to talk about how we enact that local testing into continuous integration. And then as we scale, there are some sort of issues that come at scale, and we're going to talk about how Bazel and smart test caching were used to solve these scaling problems. Start off, local testing. The point of this whole thing, we have a contract between our code and our data that is either implicit or explicit, but at the end of the day, we want to validate it. We want to make sure that the code actually matches up with what the data looks like. And most frequently, and still quite frequently, what happens is that you're going to do this in prod. You're going to write your code based on your own understanding of the data, and then you're going to put it into either a staging environment that's tested up against production data, or you're going to actually just put it up into production. And then after 45 minutes of runtime, you're going to see a surprise column not found exception. Oh, well, it was me. Now I have to make the change and wait another 45 minutes to see if it ran. This is, of course, quite a common workflow. If you can instead validate this code and data contract locally, then you have speed on your side. You don't have the I/O inefficiencies that would come with testing in prod. You don't end up with the surprise exceptions in prod after 45 minutes. Instead, you end up with them locally in about 45 seconds. Which, at the end of the day, what we really want is a faster development cycle. I make a change, I see if that change worked. I want to wait as little time as possible before I see that happen. And that's a good development experience. the way that we can do this, the way that we can validate the code and data contracts on a local machine is through testing, unit and integration testing. For those who in the audience who have had this revelation and have tried to do local testing with Spark and with databases, there's a set of common headaches that you've probably encountered at least once. For one thing, setting up local Spark is a little bit of a pain. Having a local database that Spark is going to be writing into just on everybody's machine, well, that's also kind of painful. And then you're going to have to set up mock data with mock schemas. And then you're going to have to mock the read and write interfaces, and then make sure that nothing's actually accidentally touching prod, which can tend to happen in situations like this. And then also wrap everything in a nice, clean setup and teardown phase so that your tests aren't actually touching each other. This is a lot of boilerplate, a really significant amount of stuff. And so what we've done to make this whole thing a very pleasant development experience is that we've handled it. I want to talk about exactly what that's going to look like for somebody who's writing a test in this monorepo. For example, you see this is an example of a test, at least the beginning of one. And for those of you that are familiar with PyTest, you can see that there's an argument to that function that's a Hive database. If you're not familiar with PyTest fixtures, basically what this is that for every test that's written in the monorepo, for the duration of that test, every test has its own special copy of a blank Hive database that they're free to do with what they want, and it's cleaned up afterwards. And in this case, what we're doing is, we're importing this hotels object, the hotel table as code, and we're adding it to this database. It doesn't have any data yet, but we're just adding it with the schema that we expect it to have. This fixture is globally available and erased after every single test, ensuring isolation of your tests. The most important thing here is that when you are creating mock data in your unit tests, quite frequently, you have to repeat the schema. So then when you change the schema, you have to change it twice. This is not efficient, and this is not really the best unit testing practices, especially because it leaves you open to typo errors quite frequently. You have a significantly reduced chance of typos and less development effort when you can just import the schema directly from an object. These tests naturally are going to be for some kind of ETL pipeline function. So let's see what one of those is going to look like. Let's say we've got process hotel pipeline. What it's going to do, it's very simple. We're going to load up the hotels table. We're going to then run some function that we've created called get available rooms. And then we're going to write the available rooms data frame that resulted from that function into our available rooms table. Easy. We load it, we transform it, and then we write it. So let's say that hypothetically this function accesses a num rooms column in the hotel df. And then we need to actually test this code to verify that the num rooms column actually exists in your production code. This is quite easy now, because you can just create an empty table with this predefined schema that may or may not contain the num rooms column. And then you have this that just runs the code. This is partially a power of the framework and partially one of the powers of Spark, is that you can run a test without any data. Just blank data frames with correct schemas. And this ends up being an incredibly powerful test. For one thing, it'll fail immediately if the input table has no num rooms column, which is exactly what you wanted to verify in the first place. And most importantly, there's no data needed. And that also reduces the overhead needed to create the test in the first place. And let's say, okay, well, you just said no data needed, but I actually have functionality that's required to create data. And then the other nice thing is that when we have the table defined as a table as code, we can also have a write interface to that table where we can just create data and write to it, and we don't need to redefine the table again. Most importantly, another beauty of Spark is that you don't need to write every column. Some tables have like hundreds of columns. Your unit tests shouldn't have hundreds of columns. Ideally, they only need one of them or two. So we've got unit testing. We've got unit testing and integration testing down. But we want to at least continuously confirm that these tests are being run, that they're correct, and that they're actually covering as much behavior as we want it to. And that's where continuous integration comes into play. So we use GitLab CI extensively. Some of you likely use any other types of CI. But more or less, the landscape of it is going to look about the same. We've got a testing step that's going to run automatically all of our unit tests, all of our integration tests, and check to make sure that we have coverage. That's important. I'll get on that in a later slide. And then, importantly for usability, every single time that something is merged to master, it's deployed to our internal PyPy as a new package so that all of the code that's written there can be imported and installed basically from anywhere in the company. This is a really nice experience. It reduces the need for conversations of, well, how can I install your code? Well, it's right there. It's all in the same place. One important thing here is that all the tests have to pass before we do any kind of merge to master. This is really important in conjunction with code coverage. The idea is that, in a monorepo, there's a bit of a social contract that you have. You have your code coexisting with other people's code, and you have the opportunity, if you change your code, you can break other people's code. But with this in place, we effectively prevent that. You are not even allowed to merge your code if your code breaks somebody else's. That ends up being a very important step here. Another important piece of that puzzle is 100% line coverage. Talking about coverage can be a little bit controversial, but we can at least confidently say that having 100% test coverage combined with what you saw earlier, this execution plan test where you're testing Spark with empty data, effectively it verifies more or less that the code and data contract at all times for every state of the master branch of the repository is always validated. And with that, you are free to do Friday afternoon deployments as much as you want to. And at this point, we don't even, not as much as you want to, but more often than never. So when we start talking about unit testing, there's another piece of the conversation we have to look at. That is that there are a lot of these things. If you're really passionate about unit tests, some people may have written thousands of these things. And the runtime of these gets really long, especially in a monorepo setting. So if you see thousands of tests, some of them are big, some of them are small, just running this on 1 hour can take upwards of an hour. Running this on one machine can take upwards of an hour, maybe even upwards of 2 hours. This is just unacceptable for a continuous integration pipeline. So what do? Well, we observe that not every test needs to be run on every change, especially if the monorepo is spanning a lot of different teams across the business. If I change my code in marketing, I shouldn't have to run the tests in security. That doesn't make any sense. So this brings us to talk about Bazel. For people who are not familiar with Bazel, it's basically a build system that allows you to build incrementally and only test the changes that you absolutely need to test based on dependencies that you specified. So it also allows you to specify dependencies between code explicitly. And I'll illustrate a little bit what this looks like in practice. Before using Bazel, we just represented the entire monorepo as just one package, really. One colossal Python package with a bunch of tables as code artifacts and a bunch of code artifacts. And then we test everything all the time. This, of course, ran out of its welcome very quickly as the tests quickly started to take way too long to run. The key insight with Bazel is representing every schema for your data sets and every pipeline as its own small Python package. The benefit that you get from this is that this allows you to tell Bazel, hey, pipeline X depends on table A, and pipeline Y depends on table B. Which then allows you to say, well, I only changed table A, so I only need to test these pipelines. So then you end up with, instead of your tests running in an hour, they take maybe like 30 seconds. This is really powerful and really allows us to scale much, much faster. There's an important aspect of this diagram is that it kind of looks like what the first thing that Bram showed, which is basically that before we had these contracts implicitly. and they were tested through production, taking a lot of time and only basically communicating through the errors that they brought each other. Now, this contract is represented explicitly and is able to be tested locally relatively instantly. This is a real upgrade from the old system. So all these things are great technical details, but this did not come from nowhere. Basically, surrounding the entire monorepo and the tables as code concept, there's a lot of salesmanship that has to be done in order to convince people to use it, and a lot of people involved. And that leads me to talk about community. I want to have like one point, which is that like some people might be thinking like, well, if this is so obviously better than the other solution, then why don't all the managers get together and tell the practitioners that they have to be using it starting next week? Well, the reality is that maybe similar with a lot of other companies, booking doesn't really work like that. It's very bottom up, and if we want to have people using a different product, then we have to convince them to use it. So the way it began was as a single product team. This is a really effective dogfooding strategy, because when their production pipelines were on it, now suddenly, well, you really need it to work, right? So they didn't want to spend all their time manually writing down schemas in Python classes. So they created a command line interface that allows you to pull directly from the existing schema registry and generate the classes based on the schema registry. Especially convenient when there's like over 100 columns in some tables. And really doing that for any common operation gives you a lot of extra speed up. Through the magic of how good this was for that one team, people hear about it, people sell it aggressively, and it grew kind of organically across some other teams in the similar area. And now when other people from other teams are using it, well, okay, now our knowledge is not so universal. Now we need sort of easy interfaces to things. And that's where, of course, you're running your testing. You should be providing a Docker image so that everybody can run it on their machine without having to do a bunch of setup. As it gets easier and easier to use, gets more features and more users and people talking about it, gradually it reaches critical mass. It starts growing along teams, and then we end up in a network effect situation where people are telling each other about it and other folks are using it. This is a lot of stuff to support. These are a lot of people using these things. So how do we support a community, and how do we keep growing it? And there's three main things that we do here. Communication and support is super important. For all the people that are using the monorepo, maybe they'll have bugs here and there. We routinely communicate with them through Slack and have a support channel where all the maintainers help people out. We treat it as internal open source. So like if you come in and you want to make a change, there's something that you want to add to the framework, go ahead, send us a merge request and then we'll make it happen. And then also quite importantly, we train people. We upskill people on using this framework, especially if there's a lot of new stuff to learn about how to use it. Then we bring on newcomers to this framework, and we have all-day training sessions here and there. Where has this all brought us at this stage? Well, so right now this supports 384 ETL pipelines, growing really rapidly. It's basically doubling every year. And so I wouldn't be surprised by the time I finish speaking, it's 385. So it supports about 25 teams across the company right now. It includes not just ETL, but also model training pipelines. And as a matter of convenience for people with pipelines, there's also some alerting and monitoring libraries that they can use to really juice up their workflows. Where are we looking to in the future? Well, basically growing. We want to continue onboarding teams. We want to continue onboarding more data sources. And then finally, given the potential for interest, we could maybe look into open sourcing it. And that's everything. Thank you very much.